Cool. So we spent the summer research scholarship working on the memory management inside HipHopVM, and we worked under our supervisor, Steve Blackburn. What is HipHopVM? HipHopVM is a free and open source PHP engine written by the guys at Facebook. They use it to host their internal services, pretty much the entire website. It's a mammoth C++ project, 1.2 million lines of code, and that includes mainly C++, PHP, and large amounts of assembly. It's a JIT compiler. It originally used to compile PHP to C++ and then to native code, but they figured if they moved it to a JIT, they had more room for optimizations, and they got a large performance boost out of it. It's on GitHub, and it is a monster. Our tasks within HipHop were to kind of isolate the performance effects that naive reference counting has on the overall execution and request performance, to kind of see how memory accesses to PHP objects map to physical memory accesses through the VM, and to analyze HipHopVM's internal memory management subsystems.
Right, so I'll be giving an overview of basically what HipHopVM does with its memory. HipHopVM itself has its own memory management facilities that are used internally inside the program, in addition to the low-level system calls. So at the top, HipHopVM itself has its own memory manager, and because it's written in C++, it's got access to lower-level memory via like direct access to virtual memory through functions such as malloc-free, using the JMalloc library. And on top of this, on top of HHVM, we have the PHP objects living in PHP, in the PHP runtime, which allocate and which create objects freely. And HipHop is supposed to, essentially supposed to manage that all by itself, using its own memory manager. The problems with this memory manager that basically we were tasked to view at is that the memory manager itself is not always used consistently, and it's a very, very large and difficult to understand piece of code at times. Like that's the API for the memory manager, which took us about a month to figure out. And some functions work backed directly by system functions, and some functions allocate memory on top of what they call the slab, which is a large chunk of memory allocated in advance for small objects. Some important things to note about this memory manager is that there are several types of allocations. There are several types of allocations in PHP. We have PHP objects, which live inside the PHP runtime. We have C objects, which HipHop uses to run itself, and also to coordinate the PHP object. And in addition to this, sometimes the boundaries between the two are mixed up. So HipHop might create an array which will then be passed to the PHP side. And sometimes they live in the malloc-free world, sometimes they live in the smart managed world, and so it was a bit just a bit unusual, I guess, to understand. Some important things to note is that every thread, basically as a server, has multiple threads of execution, and every thread has its own memory manager, which allocates a slab at the beginning of its lifetime, and at the end of each lifetime will destroy the slab, getting rid of all the small objects. This happens on a request-based cycle, as well as with objects getting cleaned up at the end of every request. So my job was basically to try and get a better picture of what the memory manager itself was doing, and also to see whether or not there might be some optimizations, especially because, for example, even though the manager itself, you would assume that HipHopVM would have a memory manager built specifically for PHP objects, but as we found out, that was not really the case. I developed some tools and modified the code a bit to see if we could get some statistics out of this. Like, this is just a slice-based view of HipHopVM running the WordPress blog, And this was, I took a snapshot of its memory usage over one request, which is, it looks like basically ultimately what I would have liked to have done with these tools was to have some kind of at any point using the log data, we'd be able to pipe it through the tool I was going to write and see what the memory management is composed of at any time, like what is being used for C objects, what is being used for PHP objects. So at the moment, what we can get is we can get lifetimes, we can get like object lifespan. This graph, we have the blue line is what the underlying system is doing. So this is caused to malloc free, and the red line is what PHP is doing, or HipHopVM is doing on top of their own slabs. So there seems to be a kind of discrepancy between what their code is written for and what it's actually doing. However, we're not sure of whether this is the case because we don't have access to PHP's actual the actual PHP code that runs Facebook, which may or may not have different requirements to something like Facebook. This was an interesting graph that I found that I produced during my testing. There seems to be an edge case. I used a PHP Markdown parsing library, which caused some really strange behavior, such as allocating, deallocating medium-sized objects really quickly over a period of time. The future of this project, because we are handing off to this project after we finish with this, will be handed off to a master's project for some other students at ANU. But maybe from here we might be able to optimize or retool HipHopVM to give it a more consistent interface that's more easier to reason about and has nicer behavior, faster behavior. But I will let Ben talk about that when he gets to his talk.
So yeah, my aim for the 8 weeks was to see if you could remove reference counting from PHP and see what kind of performance benefits or penalties that incurs. So the memory manager at the end of each PHP request actually frees all the memory it's allocated. So you never have an object, you very rarely have an object which lives longer than a request. So we figured if you're going to free all the memory at the end of a request, then why would you bother doing reference counting for the purpose of garbage collection? It seems kind of like flogging a dead horse. So yeah, we figured we'd try and nail down the exact penalty that these operations incur. So yeah, PHP is based on naive reference counting and explicit garbage collection. So as soon as an object's reference count hits 0, it's deallocated. And this is required by the language's semantics. I'm not sure if any of you guys saw Steve's presentation a couple of weeks ago about PHP's object semantics. It's a bit weird. It's pass by value. And pass by value, if you're passing large arrays around inside your PHP code, then you're going to be doing lots of large array copies. So it's not actually a particularly efficient solution. So what they do is they optimize it using copy on write semantics. So if you have an array here and then also assign it to a variable here, it won't actually create a copy of it until you alter the array. And unfortunately, this kind of bleeds up into how you write your PHP code. And it actually means that at any time you assign an array or you write to an array, you need to know exactly how many people are looking at it, exactly what its reference count is, which means removing the reference count from PHP is not a trivial matter. And this kind of caused issues later on in the project. And to add to that, HipHopVM does reference counting in an interesting way. They have a reference counting API called countable.h, and these just contain C++ macros which define functions which increment reference counts, decrement them, checks the current, checks if an object is referenced by multiple other objects, and then can deallocate it if needed. Again, like Nathan said, they don't quite consistently use their own APIs, so there are many places in the code where instead of using this nice defined reference counting API, they decide to just go and directly mutate the reference count, which causes problems because you end up having to track down and grep all these special cases. And then separate to that, HipHopVM is a JIT environment for PHP. So when actually running in JIT mode instead of just a plain interpreter mode, there are also a ton of sections of x86 assembly which are omitted, which deal with reference counting. So we also had to track down and remove all those. And that was easier because they're all kind of centralized, but it's actually a lot harder to work out the behavior because it's written obfuscated assembly. And the best thing is both these systems, besides sharing the actual count variable, are completely separate. So it's certainly non-trivial to remove them and keep the application running. And it's also completely separate of the memory manager that Nathan just mentioned. So you have 3 systems doing the one thing effectively. So I removed these 3 systems. I removed the countable macros which define the reference counting API. I removed the reference count related JIT operations, and I removed all the little modifications and re-implementations of reference countings throughout the code base. Comparing this new build, which I've named no count, to regular HHVM, it was largely slower. And I think this was because it had wildly different memory characteristics. So whilst the regular one spent this extra time counting its references, it didn't spend as much time allocating new slabs of memory because it was efficient enough that it could reuse them. So I still hadn't isolated exactly what the performance penalty of reference counting was in HHVM. So the next step was to kind of even the playing field in terms of memory characteristics. So I modified the memory manager to be a bump point allocator. Previously, it used free lists for small allocations and then just directly mapped to malloc calls for large allocations. So I kind of unified this, so everything's just bump point allocated, there's no freeze, and this gave me a very good kind of base case to compare my removal of reference counting to. The memory manager does a funny thing where before it clears objects, it actually calls this method called sweepable, which is kind of a chance for the objects to clean up anything that it's directly mallocked or callocked. And I start to perform these because, unfortunately, if you remove them, then you start running into errors such as database connections remain open, so your benchmarks don't run, and you can't open any more files. So I made sure all my builds still had this one feature enabled for consistency. This resulted in 2 different builds, HHVM bump and HHVM bump no count. And now the effects of reference counting should be completely isolated to the HHVM bump no count build. So I ran some benchmarks on it. The problem with these benchmarks is that they all depend on these reference counting copy on write semantics, which I'd subsequently broken. So I used a modified version of a benchmark that's included with HHVM. It has heavy memory usage, so it actually stresses the reference counting in memory subsystems. But unlike a normal PHP request, where you can execute probably several hundred per second, probably several thousand per second, sorry, this request is quite intensive. It takes a long time to execute, so it might not be typical of what a regular PHP application runs like. It's basic configuration of what I use. I just used the ANU provided workstation, and I ran various amounts of benchmarks using Apache benchmark. So just to see what the effects of the length of the benchmark versus the level of concurrency in the benchmark was. And I graphed them using MATLAB, and everything's in terms of number of requests and number of concurrent requests performed. And I came up with some lovely graphs. This graph is the amount of the request time for the lowest 20% of requests that were executed. And this graph isn't super useful because it's a very small sample size, but it does seem to show that in the lowest percentage of requests that the response time really depends on the level of concurrency and the build I was using. But there isn't really any clear data to be drawn from this. The most interesting graph from this section was actually the time taken to execute the lowest 50% of requests. Surprisingly, this blue surface, which is on top, is the one that doesn't perform reference counting. And apparently that is marginally slower than actually performing reference counting, which was a surprising result, which I'll get to in a second. Yes. And as you get up into the highest 80%, you start to get noise in because HipHopVM has a strange warm-up period. When you're running it in server mode, it starts compiling the methods and caching them. So again, there's not a great deal to show there, but it still looks like that the non-reference counting build is performing worst. And my last 2 graphs were the request process per second, and here you can see a definite difference between not performing reference counting and performing reference counting in terms of requests per second. So in this case, a higher result is better, which kind of surprised me when I got this data at the start of the week. And the same thing showed here. The execution time for my entire benchmark is always longer on builds without reference counting. I'm not 100% sure why this occurred. The data's quite new and I haven't had a chance to analyze it, but I think it has something to do with the copy on write semantics. So given that these semantics are based on whether there are multiple references to an array, its copying behavior differs. So if you only have one person looking at an array, it might actually not copy it when you mutate an element because it doesn't need to create the second copy for the copy by value semantics. But if there are multiple references to this array, then it will have to copy it on every mutation. So I'm thinking, my hypothesis is that by removing the reference counting and making the call in the reference counting API has multiple refs relatively invalid, I may have actually instigated overzealous copying of the arrays on mutation. So I'm creating full copies of arrays when really I should just be able to mutate the one I'm using in place. This could be confirmed by comparing the memory usage of HHVM bump and bump no count, because bump still performs the reference counting and shouldn't have this overzealous copying behavior. And there are a lot of, unfortunately, I spent a lot of time kind of implementing these builds to actually run PHP code. So there's a lot of questions I would like to look at, like why there was this negative result of removing reference counting, increasing execution time. I think a way to kind of analyze this would be to remove copy on write and actually make it copy on assignment. So as soon as it copies the moment you reassign an array. I'd also like to look at how the GC would work if you only cleared memory at the end of a request, because whilst it does that, it still performs callocs and frees during a request, and it might actually be a better trade-off just to keep allocating during the request and free it all at once, so you're not performing as many free operations. And it might actually result in better locality because you're not reusing sections of memory returned from the free list. And the real interesting challenge is if anyone goes forward with removing reference counting from PHP, given that the copy and write semantics are quite baked into the language, there's some funny things that can catch you with that. You would actually still need to emulate this behavior. So it'd be interesting to see how you can emulate this behavior without keeping accurate reference counts.
And I'm going to be talking about the more physical side, that when you start allocating PHP object, where it ends up on the memory and how it's... Because the HHVM machine, it needs to represent the PHP object. It's a foreign language, it needs to find some way of representing it in its own way that it can dump it on the actual physical memory. And how it does that, and how it actually translates to actual memory code. So starting with just a slab of memory, we start... this is slightly more generalized than just HHVM, but we start with a slab of memory. The memory manager Nathan was talking about assigns it, and it'll start filling it with parts of PHP. It might do a write operation there, another few starts reading somewhere, and we start breaking the memory utilization into different parts. Now, what I wanted to have a look at is which parts of these parts are actually actively written to a lot, and which parts may actually be completely empty. Just that the data structures which are being used in HHVM may not actually be completely up to date, that sections are no longer used and they're just wasting space. And because HHVM is basically built purely for performance, that can really make a difference. So I broke this into a separate section, which is from the HHVM itself. It's really easy to get what the memory was allocated. Like the memory manager, ask the memory manager, I want to have a piece of memory which is 8 bytes big. Memory manager gives you an address and where you can place your 8 bytes. Now I use this second tool called valgrind, which is basically an interceptor. I'll talk about how valgrind works in a second. And valgrind is able to tell me which pieces of memory overall the entire project were used, which ones had read accesses on them, which ones had write accesses on them, how often, when they happened, all that jazz. Combining the two, I get to filter out the left any other sections of memory which got accessed, which I don't actually care about, because I want to focus on a particular piece of memory which was allocated by by the HipHop virtual machine. So the way this actually fits together is a bit interesting. You start with the original HH virtual machine binary code. This isn't decompiled with some fancy flags. This is actually just binary code, which is interpreted by Valgrind into its own representation. And the Valgrind instrumentation is able to just follow how the binary code is working through and work out where it's going to access a piece of memory, where it's going to end up having to write something, and even the addresses which all this happens. And Valgrind is so powerful that it even gives you the option of simply modifying the code on the fly if you manage to catch something which actually that's if I want to instrument this properly, maybe I can just change the binary which is going to spew that. And then we finally get to the part where the HH machine gets to be executed, which is so you start off again, have a binary at the left, gets translated into Valgrind's intermediate representation, which then gets translated back into a binary. It tries to do its own optimizations. It tries to basically recompile the program on the fly. But this produces a few problems. The HHVM, because it has its own memory manager, is the one who has to tell me where certain slabs of memory are allocated. I can't just follow the system calls, because the system calls just will tell me, hey, I had 2 megabytes slab allocated here. And I didn't have any other allocations because that's all which got allocated. So I need the HHVM to tell me where something got allocated. But Valgrind is the one to tell me where the read and write accesses happen. Now, if you follow this chain through, that it tells me where the read and write accesses happened, and then it tells me where I'm supposed to be looking for them. And this chain is actually, I never quite managed to get this out of my system, because if the virtual machine actually allocates and deallocates inside a single superblock, as Valgrind calls them, which is that it just does it in chunks. It keeps on alternating between analyzing the code and executing the next chunk. If it manages to allocate, deallocate the same piece of execution code for of HHVM, I actually completely miss which sectors of memory I should be looking at. But for the ones which didn't manage to get by this, and I mean, you have a lot of read and write accesses. I don't have any filtered results. This is a specific size of memory subs which I was looking at, but the actual allocations and deallocations in HipHop are so all over the place that a lot of other filtering and meshing inside HHVM would be required to actually know what these different objects are. But the basic principle is already there. That I'm able to look at memory, I'm able to see where the read and write accesses happen, and I know that that this is the sum of a lot of different objects, but it's always in the same offsets of a single object. And you can follow that the front part has a lot of write accesses, but only about half as many read accesses. Maybe you can start working out whether you actually need to write this other half of the time. This part of memory doesn't seem to be used at all. It's just for some objects it may be used for some, but there may very possibly be some data structures which are completely decrepit and don't need that. They're just wasting space, wasting cache, increasing the page count, and at the end the same thing. But that is basically what I've been working towards. Sum up again, I'm using Valgrind to just look at the reads and writes, get the memory sectors from the HHVM itself, and the fact that I'm alternating constantly between executing some HHVM code and then analyzing it beforehand. And just the fact that these aren't properly synchronized is really troublesome.
So yeah, this work is leading on to a bloke who's doing his PhD, kind of working in the same areas this is. So hopefully, whilst we don't have a great deal of concrete work to kind of contribute back to the HHVM project, we have developed a really good base to start analysing these characteristics a bit better. And I guess we'd just like to thank Steve Blackburn and his entire group for giving us the chance and giving us the help we need to do this. Has anyone got any questions? Nope. Cool. Thanks.